In this video, we're going to take a look at calculating area, arc length, and slope for polar coordinate situations. So in the first picture here, I've got a picture of an area that we might want to find. And so we have a part of a circle in this case of radius r, and we have a alpha and a here an alpha and a beta angle. And so the formula to find that shaded area in between depends on how far the angle moved from alpha to beta, and we express that as an area formula, the general equation being 1/2 times the distance from alpha to beta, or integral from alpha to beta, of r squared d theta. You can also think about r squared as a function of the theta value, and then we can use polar coordinate equations in there. So for instance, the picture below, if I want to find out this shaded area on this side, and clearly, I mean, we can use other techniques, like the area below is 1/2 pi r squared, and then the radius in this case is, this is a circle of radius 2, and so I can get 1/2 4 pi, which is 2 pi. So we just want to confirm that using the above area formula. So I now know that a circle of radius 2 centered at 0, 2 has a formula for r that's r equals 4 sine theta. And so I can substitute that in. And then, so my r squared is 4 sine theta. My r is 4 sine theta, so I square it, I get 16 sine squared, pull out the 16 to get this 8, and I still have a sine squared. I don't have an integration for sine squared, so I do a substitution, a double angle substitution, and I get 1 minus cos double angle is equal to sine squared. And I can then integrate on the alpha to beta of 0 to pi over 2, substituting those in, and I can confirm that I get 2 pi for this. Let's take a look at another example. So in this case, we want to find the area between two curves. And we do it similar to what we've done in the past, where if we want to find the area between two curves, then we can take the outer curve minus the inner curve. It's just that we adapt this formula, so area is now 1/2 from alpha to beta of the difference between the outer curve and the inner curve, the f2. So this is the outer function here, f sub 2 of theta, this one, and this is the inner one, f1 of theta. And the inner one has a radius of 1, as a formula, r equals 1, and the outer one has been shifted, so we can use the formula r equals 2 cos theta for that one. And to get the shaded area, what you'll notice that we do is we take this picture here is for calculating the area between these intersection points. So there's this point here and this point here in theta for the bigger function, r equals 2 cos theta. And this picture here is on the same interval from negative pi over 3 to pi over 3 for our smaller graph of r equals 1. And then I just substitute them in. So there's the outer function, there's the inner function, and they're squared and on the same intervals from negative pi over 3 to pi over 3, and subtract the 2. Fairly similar to some of the things that we've done before, just using the new techniques for polar coordinates. And I won't solve this one for you, but I have definitely set it up there. Let's take a look at something else, which is arc length. And so the arc length formula is find the distance from alpha to beta of the square root of the function of theta squared plus the derivative of the function of theta squared d theta. So if I have, again, a circle, and this one's a circle of radius a centered at a0, where a is greater than 0. Here's the formula for that circle. I take the derivative, so negative 2a sine theta I use the inside piece of here to calculate f of theta squared plus f prime of theta squared. That's 4a squared cos squared plus 4a squared sine squared. Factoring out the 4a squared, I notice that I get sine squared plus cos squared, which is just 1. And so this is 4a squared. And then I take the square root of that when I put it into the formula. So it becomes the integral from 0 to pi of 2a d theta is equal to 2 pi a. And in this case, a is the radius. So you may recognize that formula as 2 pi r. Which is the circumference of this circle of radius r, radius a. Now, one interesting thing is you may think that this value here should be 2 pi, but let's just double check what's going on here. Okay, so let's just do this slowly and figure out where we are. When theta is equal to 0, my r value will be 2a cos 0, which is 2a. And so I am at this location, which is 2a comma 0. If we step this up a little bit and make theta 90 degrees, then I am at 2a cosine 90 degrees, which is at 0. So my radius is now 0. Well, where is that located? Well, the coordinate here is where we are with a radius of 0. We're 0 units away from the origin when we're at pi over 2. So this indication here, this point here, is actually at pi over 2. And so it turns out this point here is where we are halfway between, which is pi over 4. And so you can see that when theta is 0, we're at this location. When theta is pi over 4, we're here, 2 pi here. This is 3 pi over 4. And so we get all the way back around here, say that theta was 0, and we get back there at pi. And that's why this value here is pi and not 2 pi. So when you're doing these kinds of questions, we're not used to working in polar coordinates, so it's a good idea to check where are we, where is the value of our radius at each of the theta values, and just pick and choose some to double check so that you don't accidentally think that this is going between 0 and 2 pi. That's it for today.